want to show you two more examples of using the techniques we talked about for integrating quotients that become the form that give us the inverse trig functions. Looking at number 5, the integral of dx over x squared minus 4x plus 5. Remember the things that we think of. Can I divide into the numerator first? Well, my numerator really isn't anything but 1, so the answer for that is no. Number 2, can I do a u substitution? Well, there's nothing complicated, but I have a denominator. If I do the derivative of the denominator, I don't see anything on top. That would be its derivative. Therefore, probably second scenario is out. So the third thing I think of is this one of my inverse trig forms. And there's no square root, so I think, well, if it is, then it would have to be arctangent. But what does that mean? That means it has to look like this, the integral of du over a squared plus u squared, and I have 3 terms in the denominator. It's supposed to be a sum of perfect squares, and yet this is a trinomial with only one perfect square there. Can we make a trinomial look like a sum of perfect squares? Why, yes, we can. How do we do that? That's called completing the square. We can make a trinomial look like a sum or a difference of two perfect squares if we complete the square. So in this example, I'm going to show you how sometimes you have to think about completing the square, meaning make this a perfect square trinomial such that it can be factored into perfect squares. Let's remember how we do that. X squared minus 4x plus 5. I want to think of a way that I can factor this such that this trinomial factors into something such as x minus something or x plus something, and I'll just give this some value. Maybe I'll call it d. We use c a lot, squared. Okay, x plus some number squared. I want to make this perfect square trinomial such that it'll factor like this. I want perfect squares in my denominator. How do we get it to be that? Let's rewrite this integral so that we have a little bit more room in the denominator to work. X squared minus 4x, and I'm going to move the plus 5 off to the side a little bit. We want to figure out what's going to go in this blank right here that will make this a perfect square trinomial. When I think of factoring a trinomial, I think of I multiply two numbers to get this number, and I add the two numbers to get this. So to multiply and get a perfect square, they have to be two of the same numbers. So if two of the same numbers are multiplying to make this, and two of the same numbers are multiplying to make this, add to make this, I divide this guy by 2, cut him in half. So 4 divided by 2 is 2. That's the number that got doubled to give me 4. Therefore, that's the number that should be squared to fix this trinomial. So I take that number, square him, I get 4. So 4 is the number that I have to add here. So I'm going to say plus 4. But I can't just change an expression like that because it totally changes its meaning. If I want to add a number, the only number that I can add where the meaning doesn't change is 0. So if I add 4, I have to keep it as 0 by subtracting 4 as well. Now that I've done that, I can take this perfect square trinomial, x squared minus 4x plus 4, this 2 is just saying how to get there, and factor it. So here's what my denominator looks like now. X squared minus 4x plus 4 factors into x minus 2 quantity squared. The rest of it, those leftovers at the end here, combine to make plus 1. Do I have a sum of squares now? Yes, I do. Is my constant expression first and my variable expression after? No, but does it matter when I have a plus? can't I just turn these around like this when I'm adding? Sure I can. So now we can go to say, here's my a squared, here's my u squared. Let's write it down. A squared is 1, u squared is x minus 2. Therefore, a is 1 and u squared is x minus 2 squared. U is x minus 2, and therefore du is just dx. Now we can rewrite this as the integral of dx over a squared plus u squared, and because we've memorized it, we know that this is equivalent to 1 over a, arctangent of u over a plus c. Now we can fill in from our information here, 1 over 1 arctangent of u, x minus 2 over 1 plus c. Get rid of all those ones. We don't need them, and it's easy to clean up. Make sure you have the parentheses because all of that's in the arctangent function, and we've successfully found the antiderivative. Let's try that again, but with the radical form and a difference. I see a radical in the denominator, so if I'm thinking through my strategy of the inverse trig functions, perhaps I'm thinking that it could be arcsine or arcsecant. But I'm not really sure which one because I have variable expressions everywhere under that radical, not just first or second, but everywhere. So let's say I have an x squared and I have an x to the first. When I see that, that tells me I want to try completing the square. So I'm going to try the strategy of completing the square. Again, I'm thinking of doing completing the square when I see an x squared and I see an x to the first. Not necessarily that it has to be a trinomial, but I see an x squared and I see an x to the first. That usually tells me complete the square. X squared, x to the first usually tells me complete the square. Not always, but when those other strategies that I listed earlier don't work. So let's practice completing the square. To do that, we write the x squared first. Now I'm going to just focus on this expression here and put it back in the radical later. So rewriting just what's under the radical, negative x squared plus 6x, don't know what comes after yet. Anytime I complete the square, the leading coefficient must be positive. So I'm going to factor out the negative. What does that give me? X squared minus 6x. Don't know what comes after, but let's leave space. In fact, let's leave a little bit more space. How do I know what completes the square? I look at the coefficient of the x to the first. I divide that number in half. I divide it by 2. In this case, I get 3. I square the 3. That gives me 9. That's the number I'm supposed to add over here, plus 9. But remember, we balance it by saying minus 9 because the only number we can really add without changing anything is 0. Now we can factor. This part right here, x squared minus 6x plus 9, factors into x minus 3 quantity squared. Let's write now what we have. Notice the negatives. Negative gets distributed to this, so negative of x minus 3 squared. The negative is also for the minus 9, so that becomes plus 9. Now I don't need so many parentheses. Let's go back and put this in our integral. Dx over square root of negative of x minus 3 squared plus 9. Is this starting to look like arcsine or arcsecant? Well, remember our formulas, which one is the negative one? That's right, the negative variable expression was from arcsine. So that's what we want to try to make it look like. So we say, perhaps we turn it around even to make it look more of that form, 9 minus x minus 3 squared instead of that way. Then it looks more like the arcsine. So now we can identify our a squared and our u squared. Off to the side, let's say, okay, a squared is 9, so a is 3. U squared is quantity x minus 3 squared, so u is x minus 3. Anytime I have a du, I find its derivative, and in this case, du is just dx, because u is x minus 3, the derivative of x is 1. So that is just du. So what does this look like now? The integral of du over square root a squared minus u squared, and we know that that is arc sine of u over a plus c. Plug in our u and our a. Arc sine of x minus 3 over 3 plus c. Perhaps we want to do this, but there's our final answer. Pretty cool puzzle, isn't it?